Hello everyone. Now we will discuss different reinforcements and matrices used in composites. First I will start with reinforcement materials used in composites. If we divide the reinforcement materials as per the shapes, they are divided into three categories. First is fibers, then particles, and third one is flakes. Fibers, as we know that it is defined as that higher length to diameter ratio, length to thickness ratio. So, that is the fibers. Particles are very small in dimension, it's and flakes are a little bit larger in size. Okay. So, first let us discuss the fiber phase reinforcement. The fibers are of range from 2 micron to say 150 micron diameter. It depends on the type of materials which we use, and generally the fibers, particularly man-made fibers, are circular in cross sections, but we can get different different cross sections depending on the application. It may be tubular, hollow, rectangular, hexagonal or trilobal. There are different shapes are available, and fibers we can use depending on the application in the form of staple discontinuous form or in the form of continuous, that is filament form. And the continuous fiber, that is filaments are long, and in theory they offer continuous path by which load can be carried by composite material, and discontinuous fibers, the load is carried by the discontinuous fiber and the shared by the matrix to the transmitted to the other fiber, short fiber. The reinforcing phase can be unidirectional. So, we can arrange the filament or staple fiber in a particular direction. So, unidirectional reinforcing material is useful where we need strength in a particular direction as compared to other direction. Higher strength we get in axial direction and lower in other direction, or in the form of woven fabric where the strength or tensile characteristics in both lengthwise and crosswise are higher, but at different angle the strength of the composites are not that much as compared to the axial and cross direction. Another way of orientation is random orientation, where the short fiber, mainly short fibers, are oriented at random direction, where we get the isotropic nature as far as tensile characteristics is concerned. So, orientation of fiber is an important consideration. So, in one dimension maximum strength and stiffness are obtained in that direction of fiber, that is unidirectional. Planar in both in the form two directional strength is obtained, that is woven fabric, and random or 3 dimensional strength its isotropic property we can get from random orientation. The type of fibers we use, a wide range of fibers can be used for composite making. Most common fibers are glass fiber, carbon fiber or graphite, boron and Kevlar. They are used for high performance composite applications. So, glass fibers are most commonly used in composite, particularly a polymeric composite. The term fiberglass is applied to denote that the composite is reinforced by the glass fiber. There are different types of glass fiber. The E glass, which is strong and relatively lower cost, but modulus is low, it is less than other fiber, typically 500,000 psi. S glass, which is stiffer than E glass and its tensile strength is one of the highest of all fiber material. It is 650,000 psi. It has more than 5 times the tensile strength of the steel and has density of about 1/3 of the steel. So, it is lighter than steel and its strength is 5 times more than the steel. That is why the S glass is normally used for high strength composite application. Another fiber, high performance fiber, which is now used for very high performance composite application, which is carbon fiber. It is a combination of graphite. The graphite has a tensile strength which is 3 times to that of stronger than the steel and has a density 1/4 of that steel. So, it is stronger than steel and density is also low. So, graphite is the most stable form of carbon under standard condition. So, this fiber is very stable. Boron is also used, it is very high elastic modulus, but main problem of boron is that its cost is very high. That is why it is not used in general application, but very high end application like aerospace components we can use boron. Ceramic fibers like silicon carbide, aluminum oxide are also used. They have high elastic modulus and can be used to strengthen low density, low modulus metal such as aluminum and magnesium. Also sometime metal fibers like steel filament are used as reinforcing material for thermoplastic composite. The fibers, natural fiber, man-made fiber, and there are many varieties of commercially available fibers, that is the high performance fibers are also used. These are aramid, boron, carbon or graphite, glass, nylon, polyester, polyethylene, polypropylene are also used as reinforcing material of thermoplastic composites. So, if we see the characteristics of these reinforcing fibers, the E glass, which I have already mentioned, it is the most commonly used fiber. It is high strength, good water resistance, good electrical insulation property and lower stiffness. So, these characteristics make the e-glass suitable for reinforcement in composite. Apart from e-glass, there are other type of glass fibers available, S glass, C glass, ECR glass, AR glass. So, these are the fibers we can use for composite application. Aramid fibers, Nomex or Kevlars are used. So, superior resistance to damage, energy absorption, good in tension applications, the cable moderate stiffness, more expensive than glass. So, if we want to use this fiber for very high end application, so Nomex is normally used for high temperature resistant composites. Carbon fiber has the quality of good modulus at high temperature, excellent stiffness, it is expensive fiber, it is a brittle, low electric insulation properties. So, the brittleness of this fiber actually that is why the weaving or knitting of the carbon fibers are problematic. So, one has to take precaution to convert the carbon fiber to preform. So, these are the advantages and disadvantages of different types of fiber. So, E glass, S glass, the main advantages are high strength, low cost, but main disadvantage low stiffness and fatigue characteristics. Aramid fiber high strength, low density and it is a high moisture absorption is the main problem of aramid fiber. So, that is why the sometime the aramid fibers we have to treat with some other surface active agent. Carbon fiber high strength, that is high strength carbon, that is high strength and stiffness, the main problem with the cost. Okay. Next type of reinforcement is that it is particles and then it is a flex. So, particle reinforcing material is an important material for metals and ceramics range in size from microscopic less than 1 micron to macroscopic to 1 micron, greater than 1 micron. Within that less than 1 micron to more than 1 micron, that range it is used for basically metal and ceramic composites. In the microscopic size, the characteristics is that if it is in microscopic size range, the proportion of these particles should be 15% or less, then the particle results in strengthening the matrix. So, if we use more than 15% larger quantity of particles, lower size particle, microscopic particle, then there will be agglomeration and strength utilization will not be there. So, if we use the particle of lower size, microscopic size, then we must use with the lower proportion 15% or less. So, in that case we can utilize the strength of the particle, but in macroscopic size, if the particle sizes are more than 1 micron, then the particle that proportion should be more than 20%, 25% or more. In that case, the particle serves to share the load with the matrix material. So, then if the size of the particle is more than 20 more than 1 micron, that is it is a larger size particles, then the proportion of particles should be more, and in that case it will distribute the load, it will start sharing the load. The form of composite strengthening occurs in cemented carbide. So, this that is a cemented carbide which in which the tungsten, the matrix carbide 80% is held by the cobalt binder. So, this type of matrices are used. Carbide is a carbon compound with non-metals such as boron, calcium or silicon, or metals such as cobalt, titanium. Okay. This type of matrix. So, this is the matrix, and carbide, the carbon is a particle. So, carbon particle is used with all this type of metal and non-metal matrix. So, metal carbide are characterized by their extreme hardness. So, if we use the carbon compound, carbon particle with a metal, the metal as matrix, it will enhance the hardness. So, this metal carbides are characterized by their extreme hardness and resistance to high temperature. So, that composite become very hard and it will become resistant to high temperature and are used as abrasive, cutting tool, drill, grinding, polishing tools. So, the characteristics of this all these products, all these equipments are, it should be very hard, very it should be harder than other material, like polishing tools, it should be harder than the material which you are polishing. Basically, if you are trying to polish the iron, so it should be harder than that. So, that it will grinding, it should be it in the cutting tools. So, we use this metal matrix compound. Another types of particles are the larger particle which is known as flakes. There actually it is a 2-dimensional particles ranging from 0.01 to 1 millimeter, it is a large size flakes. This flake, it has thickness of 0.00 millimeter. So, these are used as the reinforcing phase along with other polymers also. Normally, these flakes are used with as reinforcing material, and polymers are used as the matrix material. The system of composite making from flakes are simple. The process scrap is grounded in a grinding device which chips the parent composite into flake of a broad size distribution. Like if we get, suppose you have one component here, it is a composite, suppose it is a used composites. Now, we have to grind it, make it smaller particle, break it. Normally, we can use say thermoset matrix for reusing. So, this is actually, then what we do, we mix with the this we mix with the polymer. So, this is the polymer and there we are mixing with this. After that we send this thing into mold. There is a mold and we are this material is coming here in the mold with the flake, depending on the size shape we can make, and ultimately we will get, we remove the mold, then we will get, say this is the flake composite. So, in this way first you have to crush it, okay, break it to smaller flakes, then we mix with the matrix material and then we use the mold. In this way we use the flake as reinforcement in the composite. So, the parent composite into flakes. So, initially the parent composite is normally we are talking about the thermoset matrix. So, which we can actually chop it to make smaller flake. The flakes are then sieved into different classes of sizes. So, we are actually we use a sieving and we to actually segregate different sizes depending on the size requirement, then we take the particular size and then mixed with the at different proportion to have specific strength properties. The mold is filled with the flake and matrix in a molten state. So, we can use thermoplastic matrix also here, molten thermoplastic matrix, then we mix with the flakes to get the mold, and then we dry it, okay, to get the proper composite. The mold is closed and the process cycle with the designed parameter like pressure, temperature, cooling rate is executed. So, to get final composite, and after that to eject out of the mold and to get the composite. So, what we have discussed till now, the reinforcing component. Now, we will discuss the matrix phase. Okay. The matrix phase, polymer matrix we are talking about. Polymer matrix is divided broadly into two categories, as I have already mentioned. One is thermoset, another is thermoplastic. The thermoset matrices, this undergoes irreversible chemical curing reaction and it forms crosslink for its geometrical stabilization. That means, once the crosslink is formed, it is totally stable, it is irreversible, it cannot be reversed, we cannot get the initial material. So, once the curing is done, then we cannot go back to this liquid or viscous stage. The most commonly used thermoset matrix for composites are polyester, unsaturated polyester, vinyl ester, epoxy which is widely used, phenolic ester and polyurethane. These are the thermoset polymers. Among thermoplastic polymers, basically thermoplastic is with the characteristics is that with the temperature it melts and on cooling it again solidifies. So, this is totally reversible physical changes, there is no chemical linkage taking place during this process. Most commonly used thermoplastic matrix materials are acrylonitrile, butadiene styrene which is known as ABS, polyamide that is nylon we can use, polyethylene, polypropylene and PET, polyethylene terephthalate, that is it is in its unsaturated polyester, this is saturated polyester. So, normal polyester we use, it melts and in on heating and it is actually it solidifies on cooling. So, if you see the advantages of thermoset matrix, because at present most of the actually I can say majority of plastic composites are thermoset composites basically. These are due to that it is a thermal stability is there, it is these are chemical resistant, reduced creep and stress relaxation, lower viscosity. So, it is excellent for fiber orientation. So, very low viscosity at lower temperature. So, it can penetrate through the reinforcing material very easily and it is very common material with the fabricators. So, because this does not need any special process, that is why thermoset is very popular in matrix manufacturing. As far as thermoplastic is concerned, they are actually room temperature material storage. So, you can store the material at room temperature, which we cannot do for thermoset matrix. Rapid process and low cost of forming, preformable we can make preform, and most important advantages of thermoplastic material matrix is that it is a these are excellent fracture resistance and excellent toughness. So, among the thermoset matrices, the unsaturated polyesters characteristics are low cost, extreme process versatility, its performance is good, and this polyester thermoset matrix are used in transportation industry, construction and marine. Vinyl ester, its characteristics are similar to polyester, excellent mechanical and fatigue properties, excellent chemical resistance, and its major uses are corrosion application, where the chances of corrosions are there, pipes, tanks, ducts. So, all these places we use vinyl ester as matrix material. So, synthetic the composite pipes, tanks and ducts, where corrosion chances of corrosions are there. Epoxy resins, they have excellent mechanical properties, good fatigue resistance, low shrinkage, good heat and chemical resistance, and major applications are fiber reinforced polymer strengthening system. So, where the reinforcement is required, we can use. So, there are these are the applications: reinforcing bar, phenolic matrix material, thermoset matrix, excellent fire resistant. So, in case of the where requirement of fire resistant products are there, so we can use phenolic matrix, low smoke and toxic emission. So, high strength at high temperature. So, that higher temperature application we can use. So, mass transit, ducting, fire resistant, high temperature application. Polyurethane is another thermoset matrix. The characteristics is the tough material, good impact resistance, good surface quality. So, polyurethane matrices are used in bumper beams, automotive panels. So, there we need toughness and good impact resistant characteristics. So, that is why they in those places polyurethane thermoset matrix are used. So, in short, we can say the polymers which are used for matrix, they have wide variety. So, we can select the type of polymer based on our requirement. So, they are selection based on physical and mechanical properties of the product and fabrication process requirements. So, the type of product we require or type of the facilities, manufacturing facilities available. So, based on that we select the polymer matrix, whether it will be thermoset or thermoplastic or what type of mechanical characteristics we require. Depending on that we select our polymers. Now, I will discuss the theoretical aspects or mathematical approach to calculate theoretically, at least to predict the stiffness of long fiber composite. Here we will try to discuss the measurement or predict the Young's moduli in terms of axial direction and cross plane direction. The axial and transverse Young's moduli can be predicted, it can be predicted using a simple slab model in which the fibers and matrix are represented by parallel slab of material with the thickness in proportion of their volume fraction. F is the fiber volume fraction and 1 minus F is the matrix volume fraction. Now, let us see what the model is telling. Suppose this is a matrix. Here we have fibers. So, fibers are there. Now, if we take the actual volume of fiber say V f, okay, and total volume is say 1, volume fraction of fiber is V f. So, 1 minus V f will be the volume fraction of the matrix. So, in this model what we do, we can now let us draw once again. Now, this is the thickness say V f. Okay. Now, here this portion it is a fiber portion. And this portion is the other portion, this is the matrix portion. This one is the matrix. So, 1 minus V f. So, that means this in this model the volume fraction for unit cross sectional area. So, here it is a thickness is the this much is the fiber and here it will be the matrix material. So, this parallel slabs of materials. So, it has been assumed that the matrix are made of 2 parallel slabs, no sorry composite, it is a lower portion in green color I have shown, it is a fiber of volume fraction f, that is it is shown by the thickness f, and 1 by f is that the matrix. There are 2 models, one is by axial loading, it is called Voith model, another is transverse loading. I will discuss transverse loading separately. In axial loading, this is the composite block, the black lines it is a fibers, reinforcing fibers, and the yellow portion it is a composite, sorry it is a matrix portion. And when these are axially loaded, that means the elongation of fiber, elongation of matrix and elongation of the composite, they are exactly same, because they are loaded axially. So, epsilon 1 is the, this is the elongation of composite in length direction, and we will discuss epsilon 2 will be the elongation in cross plane direction or transverse direction. So, epsilon 1 equal to epsilon 1 in fiber direction fiber. So, this is the axial elongation of fiber, which is the ratio of the stress by the modulus of fiber, which is equal to the elongation of matrix, and that is equal to the stress by modulus of matrix, and it is equal to the stress by modulus of the composite. So, with this assumption if we see that the stress modulus of fiber is much more than modulus of matrix, which is basic assumption, which is actually we require, because fibers are much stiffer than matrix. The reinforcement fiber is subject to much higher stress in this case, because of the higher stiffness of fiber. So, that means stress of fiber is much more than the stress of the matrix, and there is redistribution of the load. So, load redistribution will be there. Overall stress on matrix sigma 1 can be expressed in terms of two components. One is their based on their volume fraction, that is the 1 by 1 minus f, that is volume fraction of the matrix multiplied by the stress on matrix plus volume fraction of fiber multiplied by stress on fiber. So, from there we can arrive at that the modulus, Young's modulus of matrix is the as proportion of their volume fraction of matrix and the fiber. So, 1 minus f is the volume fraction of matrix multiplied by the stiffness, that is Young's modulus of a matrix, plus f volume fraction of fiber multiplied by stiffness of fiber. So, this is known as rule of mixture, and it shows that the axial stiffness is given by a weighted mean of stiffnesses of two components depending on the volume fraction of fiber. That means, if we increase the volume fraction of fiber, if f is increased, then the stiffness of the composite will increase, because this f, this EF is much higher than the modulus of matrix EM. So, it is directly proportional to the volume fraction of fiber. Another model which predicts basically transverse loading, it is a Rios model. Here the stress acting on the reinforcement is equal to the stress acting on the matrix, that is equal stress. In earlier case, it was assumed that strain of matrix is equal to strain of the fiber. Here stress is assumed to be equal, the stress on composite is equal to stress on fiber equal to stress on the matrix. From here we can derive that elongation is in proportion of the volume fraction of matrix and fiber. So, the net strain is the sum of contribution of the matrix and the fiber. and from here we can derive initial modulus, that is of composite in transverse direction is given by the this relationship f by E f plus 1 minus f by f to the power minus 1. So, this we can derive. This is known as the inverse rule of mixture, but this assumption, this has poor estimation of E2, that is transverse stiffness. Why? Let us discuss here. Now, suppose this is a matrix, okay. Here we can have fibers in this fashion, okay, or in this fashion. When we are applying load, maybe tensile or compressive. So, in this case two things may happen. One, the fibers and this portion is matrix portion, these are matrix portion, in between the fibers they are matrix portion. Okay. Two things may happen, either, okay, let us see here. Okay. So, in reality the regions of matrix in series with the fibers, that is these are the in series with the fibers, close to them in line along the loading direction. So, when it is in line along the loading direction, these are actually subjected to higher stress. That means, the matrix portion in between the fibers will be subjected to very high stress, because they are in series. But in other places where the regions of matrix are in parallel, this is in parallel, when the loading is in this direction, in those places what will happen? The majority of the load will be carried by the reinforcing material. So, the load on matrix in between this reinforcing zone will be low. So, with the fibers adjacent laterally it is adjacent, are considerable are constrained to have the same strain as that of fiber and carry a low stress. So, the matrix in this zone is carrying lower load, but on the other hand matrix just above these fibers are carrying high load. So, that this will create actually non-uniform distribution. Now, let us see here, suppose I am drawing fibers here 1, 2, 3 fibers and 1, okay. Now, suppose we are applying load in this direction. This is the direction of load, these are the fibers, okay. And I am drawing matrix in purple color, these are the matrix in between them. So, when the load is being applied in this direction, so this fiber and this matrix, the matrix in these two positions or this portions, these matrices are subjected to high load because they are in series with the fiber. But on the other hand, the matrix parallel to fibers, these matrices, they are not subjected to high stress because the load is being shared by the reinforcing material. So, adjacent matrices in two different zones which are very close are where the load distributions are totally non-uniform distribution. That makes this model total unstable model. So, this leads to non-uniform distribution of stress and strain during transverse loading, which means that the model is inappropriate. The slab model provides lower bound for the transverse stiffness. So, transverse stiffness, the transverse stiffness measurement is difficult by this type of model, but it predicts the longitudinal stiffness well. Now, coming to the critical length. Critical length is nothing but the length which is required, minimum length required before when we try to pull, that it will below that length the fiber can be pulled out, and just above that fiber will be broken before it is coming out from the matrix. So, that critical length is important, it is very much important for short fiber composite, and it depends on the shear stress between the fibers and matrices. So, let us say this tau I is a shear stress and sigma f is the axial tensile stress on fiber. So, when the fiber is stressed with sigma f and the small fiber length is dx. So, this is actually given by, and on the other side the stress will become sigma f plus d into sigma f. So, that much increase is there. So, delta d sigma f. So, sigma f plus d sigma f. So, this is increase in the stress component. So, sigma f plus d sigma f. So, this multiplied by the cross section, this cross section of fiber equal to this cross section, this stress plus the shear stress into the this surface area, total surface area. This is the equation, balancing force, and if we simplify and integrate, we get this equation. So, this is the equation. So, sigma f equal to 4 tau I by d, where and it is x, okay, where this x is the critical length. So, the critical length is the maximum embedded length of fiber that can be pulled out from the composite without rupture. As I have mentioned, if it is more than the critical length, that fiber will not be pulled out, it will rupture. Next class I will discuss how to predict the stress of matrix, knowing the stress strain behavior of matrix and fiber. So, how to predict the stress of the composite if we know the stress strain behavior of matrix and the reinforcing material. Till then, thank you.